Okay, let's look at this next Excel calculator. In this one, again, I want you to make it as clean and perfect as possible. I've got Greek characters here for delta, D, P, and H, as they have in the Hansen Solubility Parameters workbooks and handbooks and the ebook. I'm using VM for molar volume, delta T or delta total for the total solubility parameter. I've got the equations here, the thermodynamic equations. Notice these are actually inserted equations. So you can come up here and you can do insert here, and you can do equation, and you get this little equation field in the middle. And let me get it to where you can actually see it. And then you have this equation ribbon up here that you can use to add in, integrals or whatever. There's a lot of handy little autocorrect items. Like if I wanted to do, let's just edit one of these. Let's do the delta H of mixing equation. So you do backslash capital D delta. And when you hit space, it substitutes that word for the delta figure, capital H. If I want to do subscripts, I use the underscore, and I can type in MIX. And when I hit space, it takes away that underscore and drops in mix. Let's say I wanted to actually use the standard indicator of 0 with a superscript 0. I use the caret and type 0, and then when I hit space, it like converts that over to a superscript. It equals the Greek character phi. So if I use a capital P, it gives me a capital Greek character. I don't want that. I want the lowercase. So I'm going to use lowercase p, hi. I want a subscript a, and then backslash phi, and subscript b, and then capital V, subscript tot. When I hit space, it makes it a subscript. And then I want to open, close, parentheses. When I hit space, it opens up with a little gray box that I can enter things in. Delta, so that's the lowercase delta, subscript a, minus, backslash, delta with the lowercase d, underscore b, gives me the subscript b. And I come outside the parenthesis, and then I do a caret 2, and there's my delta H of mixing equation. So this is a great way to add equations. Now I can use these corners to make it bigger, but it doesn't seem to change the font size. So if I select that, I can come up here and click up and down on these fonts because I adjusted it. Anyway, so I could also use the Control, Shift, greater than and less than symbols to increase the font size. Okay, since I've already got these up there, I'm going to delete this one. But that's how I generated these equations. I've got my gas constant here, and then what you have is the instructions for the user. Enter the Hansen solubility parameters and molar volumes. So I go to my database of Hansen solubility parameters, and I put in these two, one for methanol, one for cyclohexane. Got the units in here, you can see. I go ahead and calculate the total, because that's going to be needed for the delta H of mixing equation. So I've got the sum of squares, so it's going to square each of those values and add them together, and then take the square root. So that's my total Hansen solubility parameter, also known as the Hildebrand parameter. I calculate my mole fractions of A and B, like I said, at 5.05 increments, so I have 20 lines, and then I calculate the volume fractions. Okay, so think about this. I've got this relative number of moles here for XA. That's going to be times the molar volume of XA divided by the moles of XA times the sum of those two, I'll say. So let's look at this formula here. So I've got the molar volume of A on top, the relative molar volume of A, divided by the molar volumes added. So the A molar volume and the B molar volume total. So that's my volume fraction. And is it really that big of a deal? Well, it is if you have dramatically different molar volumes. So in this particular mixture, it's a pretty big deal. Methanol has a molar volume of 40 mils per mole, and cyclohexane is, it's much more than that. It's much more than double that. So if you wanted to just check that, here's a plot of the volume fraction versus the mole fraction. So you can see, I mean, actually, that's actually the molar volume versus the mole fraction. Let me actually plot what I'm talking about. So I'm going to change this data up here from this column to this column. So this will be the volume fraction of A versus the mole fraction of A. Yeah. Let me get rid of this chart. They both go from 0 to 1. Okay. Let me just clean this up. But notice it's not linear. They're not exactly the same. So mole fraction on this axis, volume fraction on that axis. It's not a straight diagonal line where they would be the same. The volume fraction is a slightly different function than the mole fraction. It's an important piece of this puzzle. Okay, so I've calculated my volume fraction columns. I can use the volume fractions to give me the relative amounts of D, P, and H values in the mixture. So look at this equation. I've got, oh my, I may have discovered an error. Yeah, so the mixtures are the volume fraction weighted averages of the D, P, and H values. So this should actually be the volume fractions. Interesting. Okay, so let me do that up here too, and then I'll copy it down. Yeah, so my D, P, and H values should be the volume fraction weighted averages. Okay, so let me do this for all three of these. I don't know how I made the mistake. Okay, so this is the P value and the H value. Excellent. All right, so those are my D, P, and H values. So it's the volume fraction of A times the D value for A plus the volume fraction of B times the D value for B. So you can see those cells there. Might be easier if I double click up here. Yeah. So you can see it's the volume fraction of A times the D value for A and the volume fraction of B times the D value for B. P, same kind of thing, but now it's multiplied by the P values, and H, same thing, multiplied by the H values. And in volume total, same thing, multiplied by the molar volumes for each. So that's pretty easy. My Hansen solubility parameters and molar volumes are calculated for each of the blends. We have 20 different blends. Really, we have 2 pure solvents and 18 blends. Okay, we're going to look at this chart last. So I'm going to scoot it out of the way, and let's look at this one. I'm going to move this one over. So let's calculate our entropy of mixing. Okay. So our entropy of mixing equation is given up here. It's I'm going to leave it in a per mole basis, so we'll just leave R. We won't have N in front. So if I double click this, okay. So let's look at the second value. It's that B3, that's R up here, okay, times the mole fraction, not the volume fraction. The mole fraction of A times the natural log of that mole fraction plus the mole fraction of B times the natural log of that mole fraction. Okay, all of that in parentheses multiplied by R, change the sign, we get the entropy of mixing. You see all of the entropies of mixing are positive. You did this in class for these two solvents. You got 5.6 because it was a 60-40 mixture. So this checks out with what you did in the Excel exercise in class. Now, if I were to calculate the one for 0, then one of these logs is 0. And the natural log of 0 is like negative infinity. and the natural log of 1. So this mole fraction 1 gives us 0. And so let's just set this one to 0. We're not mixing anything because it's a pure solvent, so we can't have any entropy of mixing. So we're going to set that to 0 entropy for the pure substance. We'll do that the same thing on the other end too. If we were to calculate that value there, we get an error. And so we're just going to set that as not a mixture, so the entropy of mixing is 0. Okay, so hopefully you understood that. Let's calculate delta H. So again, if we look at the formula, it's those volume fractions. Whoa, what happened? Okay, so it's volume fractions times the total volume, which we've calculated here for every mixture, times the difference in the solubility parameters, the total solubility parameters, squared. So that's what we have. So I can click on that formula and you can see them. So it's the volume fraction for A, volume fraction of B, total volume for that particular substance, which is a pure substance in this case. For the others, it's a mixture, times the difference. Now, it doesn't matter which order you do the difference because it's squared. So, you do it one way, it's positive, the other way, it's negative. But since it's squared, it doesn't matter the order of A or B. So, anyway, don't have any angst over that. You copy that formula down, and we have the delta H of mixing. Now, delta G of mixing, we need a temperature for the delta G, right? It's delta H minus T times delta S. So here's the temperature for this Gibbs energy. And so we've got this. And so it's delta H minus T times delta S. And we copy that down. So we have S, H, and G. Now, I'd like to compare H, the entropy and the enthalpy term, but I really need to compare the entropy term after it's multiplied by T. And so that's what I have over here. I have the T delta S piece. And so I wanted to plot the T delta S piece and the H piece and the Gibbs piece. So that's what this plot is right here. So I've got the delta H of mixing in red, the entropy of mixing times temperature in green, and you see how those are in competition. If the entropy of mixing is especially low, because I have a high temperature, then I get a negative delta G overall over this whole area. If I bring that down to, say, 550, I've got an area where the Gibbs energy is negative, then an area where the Gibbs energy is positive, and an area where the Gibbs energy is negative. Okay, that's interesting. So I've got a two-phase liquid here, a heterogeneous mixture here, because the Gibbs energy of mixing is positive. It's not spontaneous. But over here, I've got a homogeneous mixture. The Gibbs energy in this area is spontaneous. I can lower the temperature to room temperature, 298. So at 298, I've got a little bit of a spot where you might have some, let's see, what is this? This is XA on the x-axis. So you got a little bit of methanol contaminating the cyclohexane, and it's homogeneous. But for the most part, I'm going to have a two-layer liquid if I try to mix cyclohexane and methanol. Okay. So that's pretty cool. Now, if I take these points right here like this, that 0 point is the upper critical solution temperature for that particular mixture, around 0.2 methanol. That's a boundary of the homogeneous and heterogeneous. If I were to solve for that temperature where delta G is equal to 0 for all of these mixtures, I get the whole plot, the phase diagram plot of the upper critical solution temperatures. So that's what this column is. Now again, it only applies to mixtures. It doesn't apply to the pure solvents. And so that's why I have not calculated it for 0 or 1 mole fraction. But this is just simply the delta H of mixing divided by the delta S. If you look at this Gibbs energy equation, if I set this equal to 0, then I can move this to the other side, and I can divide both sides by S, and I've solved for the temperature at which the Gibbs energy is 0 for every mixture. So here are my temperatures, and that's what this plot is. This is the phase diagram for this mixture series of methanol and cyclohexane. And above that line is the homogeneous liquid phase, and below that line is the heterogeneous liquid phases, a two-layer solution. And if I'm at a temperature like 600, I've got a point here and a point here. On the right of this, where I've got mostly methanol, it's homogeneous. If I add a little too much cyclohexane, then I end up with two layers. But then if I keep going and add more cyclohexane, it goes back to one layer. So I have a hexane-rich layer and a methanol-rich layer here. If I'm down here at like 520 or so, then I've got still two layers, but they're more separated. The methanol layer is closer to pure methanol, and the hexane layer still has a lot of methanol in it. It's more than 50% methanol. So these are the interesting behavior. Even though you got two layers, that cyclohexane layer is not even mostly cyclohexane. It's a little more. It's actually 60% methanol. But yet it's different enough that it's a heterogeneous situation, a heterogeneous mixture. Now this is such a cool tool because I can come up here and I can change the solvents, and I can get all of their solution behavior, whether they're going to be whether it's going to be homogeneous. I can type in the temperature and see what the phase behavior will be. I can look at this chart and see where the temperature will be. So right here, if I look at 298, which is close to 300, I come over here and I know I have a two-layer solution if I go above like 19% methanol. But if I stay below 19% methanol, I can keep a homogeneous mixture. So that's a really great miscibility and TX phase diagram tool that you can make for this course. I hope you enjoy playing around with it. Once again, I want to see superscripts, subscripts, Greek characters, all of those kinds of things. We don't have any if-then statements in this particular tool or VLOOKUPs. So you're getting to know a lot about Excel and learning a lot of tools, and you've got a couple of weeks to finish these projects. Thanks.